Hey folks, Todd Coburn here from Cal Poly Pomona with your Aerospace Structures series. This lecture is for statics and it's focused on vector cross products. We're going to need these in order to calculate moments for statics. Let's take a look at how it works. So first, let's review some basic principles of vectors that we've probably seen before in physics and other courses. When we look at a moment, we're going to be ending up taking a cross product. A cross product is called a vector product or a cross product, and it has the idea of a mathematical operation that we apply to two vectors. When we cross those vectors, we're going to take the one, do a mathematical manipulation into the other to get a third vector. This applies to countless mathematical operations and engineering applications, but for our purposes, it's going to be one of the tools we're going to use to analyze what the moment is when we have a more complicated vectors occurring in space. Okay? Basically, when we have a vector, vectors have magnitude and direction. When you take the cross product, we'll be using our right-hand rule for how we put these vectors together. Let's imagine a couple vectors in a plane, P and Q we'll call them, and let's say they have an angle theta between them within that plane. When we take the cross product, we're going to find that the cross product of those two vectors gives us that third vector that we're showing as V, and it happens to be perpendicular to both vectors. That means if we have one vector, that's just a line quality. And if we have another vector, that's another line quality. But those two vectors make a plane. Whether in this plane or this one's like this, if you lay it at that angle, that's also a plane. When we take the cross product of the one vector with the other, we're going to find out we get a third vector that's perpendicular to both, which means it's perpendicular to the plane that those vectors lie in. The orientation of that vector we will find through the right-hand rule, where you can use our right-hand rule to point in the first direction, wrap toward the second direction, which will provide our third direction. It's called a vector cross product or a cross product. Now, this vector product of two vectors, P and Q, is defined as follows. The line of action of the new vector, as I said before, is going to be perpendicular to the plane that contains those two vectors. Any two vectors create a plane. Well, if they're collinear, they don't, right? But then this won't work. If we have two non-collinear vectors, they're gonna lie in the same plane. Actually, two collinear vectors do also. When we take the cross product of them, the cross product will be perpendicular to both, or perpendicular to the plane that those lie in. Next, we're going to find out that the magnitude of that cross product is that magnitude of the first vector P times the magnitude of the second vector Q times sine of the angle between them, theta. And the direction for that resultant vector from the cross product is going to be perpendicular to both. Don't worry, we're going to keep looking at this. A couple operations we're going to need. Vector products are not commutative. This means, however, Q cross P is equal to the negative of P cross Q. What this means is, if you take P crossed into Q, you're going to get one vector. And if you instead take Q crossed into P, we're going to get the exact same vector, but the negative of it. These operations are distributive, which means if you take Q plus Q1, two vectors, Q1 and Q2, add them together and take the cross product of P with that addition, you'll find out that gives you the same result if you have P cross Q1 plus P cross Q2, and they're not associative, which means if you have P cross Q cross S, you can't just take the brackets here and move them over to here. It doesn't work that way, okay? So these are just some rules that we have to live by, just like the laws of the universe. These are a few of the rules we need to deal with when we're dealing with cross products. Okay, Now, a lot of times when we first are introduced to this in physics or linear algebra or other classes, they're going to focus on a little mathematical manipulation of setting up the vectors that are involved. This is the way I learned it, and a lot of students learn to use it without even wanting to know or understanding or even caring why it's true. But actually, it's pretty powerful when you understand the basics of what it's really doing. It all roots down to some definitions. It boils down to some definitions of the unit vectors and how operations on them are defined. So remember, a unit vector is a vector that has magnitude 1. And a lot of times in mathematics, we will use unit vectors to define directions of things because we can use them, since the magnitudes are all 1, we can use them to do operations in 3 space without changing the magnitude of those vectors that we're acting on. So let's just say we have an XYZ coordinate. We defined our unit vectors in the coordinate directions. I is in the X direction, J is in the Y direction, and K is in the Z direction. This is very common. The way we're going to define these operations, if we have, remember we're talking about unit vectors, I crossed with I is going to be defined as 0. So anytime we take the cross product of I with I, any vector crossed with itself, the cross product is 0. That means I cross I is 0. This means J cross J is 0. This means K cross K is 0. Any vector crossed with any other vector is going to follow some specific rules, and it's going to follow the right-hand rule. So if you take a look at this little figure, we have X, Y, and Z. We can see if we take the I vector and cross it with the J, the way we're going to do this, we're going to use our right hand. Regardless whether you're right or left-handed, you must use your right hand. We're going to poke our fingers in the direction of the first vector of the cross product. In this case, it's I cross J. So we're focused on the second line on the left, I cross J. We poke our fingers in that direction. Cross with K, we're going to wrap our fingers toward the K, I cross J, toward the J direction, and our thumb is pointing in the third direction, the resultant direction, and that is defined as K. So a unit vector I crossed with a unit vector J gives us K. If we take the cross product of I with K, we're going to take our fingers, we're going to point them in the I direction, and then we're going to wrap them toward the K, which is coming back here, and that tells us, now we see that our thumb is pointing in the negative J direction, that tells us that I cross K is just minus J. Take our hand again. We want the cross product of J with I. We're going to take our fingers in the J direction, crossed with the I direction, which is over here, which tells us that our thumb is pointing in the resultant direction, which is in the minus K. We already said J crossed with J is 0, so J crossed with K. We're going to go in the J direction, cross it with K. We find out that gives us a positive I. K cross with I gives us a positive J, and K cross with J gives us a negative I. See how that works? It's pretty simple. You actually can do all vector product operations by following the rules from the last slide and following this process here. Okay? All right. Now, a lot of times textbooks will use this little circle. They'll draw out 2 little circles. They'll show I, J, K in the circle, and they'll have one little operation going this way and another little operation going the other way. And if you look at the little notes there, it says the unit vector read as positive if you're going from I to J to K. So if you're crossing I with J, or J with K, or K with I, then it's positive. And if you go in the opposite direction, K with J, or J with I, or I with K, then it's negative. This is how a lot of students learn it. Not in my opinion the easiest way or the best way to learn it, because now you get this additional rule. It's a lot easier, remember, I cross I is 0, J cross J is 0, K cross K is 0, and everything else is defined with a right-hand rule, poking your fingers up the rear end of the first vector and wrapping them toward the second vector, looking at the direction of your thumb to find the orientation of the resultant vector. Now, if this isn't clear, let's just do a review of what the right-hand rule is. And if you've ever taken martial arts, this is your key, okay? So Bruce Lee was the master of this idea. Basically, what you're going to do is going to strike your martial art pose, and you're going to put your hand as a weapon like a blade, okay? You're going to take your bladed hand, and you're going to jab your fingers toward the first direction. So remember, if we're doing like the I cross J, we're jabbing them down the I axis, our first vector. We then, and we're going to say, ha, in the first direction. Then we are going to wrap them toward the second. If we're going I cross J, we're going to go I, ha, and then we wrap them toward the K. Now, if you got your hand the wrong direction, we say, oh, wait a minute, J's up here. We rotate our hand, wrap them in the J direction toward J, and that tells us we're going to say cha. And then we're going to poke them in the eye of the enemy and say ka. And that is our resultant direction, and in this case, it's the K vector. This is the Bruce Lee approach to applying the right-hand rule for cross products. Okay. So let's take a look at taking the cross product of P and Q using the rules we just learned. P is a vector. It has a component Px, a component Py, and a component Pz. Px is in the I direction, Py is in the J direction, Pz is in the K direction. So when we take the cross product, we really can look at these components, Pxi plus Pyj plus Pzk, crossed with Qxi plus Qyj plus Qzk. Let's use our operations that we just learned and see how this works. So this operation then is going to mean we're going to take Pxi crossed with Qxi. Now we know the cross product of I with I. Well, we'll get to that in a minute. We're going to plus, we're going to have Pxi crossed with Qyj plus Pxi crossed with Qzk. Then we have Pyj, that's the second term, crossed with Qxi plus Pyj crossed with Qyj plus Pyj crossed with Qzk plus Pzk crossed with Qxi plus Pzk crossed with Qyj plus Pzk crossed with Qzk. This means we have Px Qx I cross I plus Px Qy I cross J plus Px Qz I cross K plus Py Qx J cross I plus Py Qy J cross J plus Py Qz J cross K plus Pz Qx K cross I plus Pz Qy K cross I. Let's k cross j plus pz qz k cross k. Okay? Now we already know when we take the cross product, I cross I is 0. And so we have this term is gone. The second term, so we end up with the second term here. That means our next term, I cross j. So we take our bladed fist, I cross with j, that's positive k. So our first term is px qy, and that's just going to be k. Our next term is this one here, plus this is pxqz, I cross k it looks like. So I cross with k is negative j. So let's put a j here, and let's make this a negative. Okay? Our next term, that's that guy. Now we're on this term, so we have p y q x, and it looks like it's a j crossed with a, what is that? J cross with I. That's a j cross I. J cross I looks like it's minus k. Minus k. Then we have py qy, j cross j, we said that's 0. Right? Over here we've got p y q z, j cross k. J cross k is going to be positive I. Positive. Then we've got this term here, p z q x, and that's k cross I. K cross I is positive j. And then we've got pz qy, and this is k cross y. K cross y is minus I. Minus I. Okay. We should have 2 of each of these terms. So it looks like we have an I term here equals, so we have p, this term here is py qzi, and then we're just going to, let's leave the I off. Let's say, let's do it again, py qz, and then we've got this other I component minus pzqy. All of those are times I. And then we have our j components, which is pxqz, that's a minus. And we have our other j term is here, pzqx. All those are j. And then we have one more term, and we have pxqy. Whoops, forget that deal there. Minus, and our other k looks like it's right here, py qx k. So our vector is equal to this time in the I direction, this in the j direction, this in the k direction. That's how we can do this using this operation. Now it's a little sloppy because I've got this slide I'm working with on your paper. You're going to have to be really careful not to make little algebraic mistakes. It is useful to go through that process at least once to make sure you understand it. There's actually an easier way to do these, and it's probably the way that you learned in your physics or whatever other classes where you had this before. But before we do that, let's go ahead and take a look at how we did. This is how that multiplies out, and this is the final vector determined exactly like we just did it, okay? So the first way is to multiply that all out like we just said. The second way is just put your I, J, K, and then right below it you'll take the first vector. In this case we're doing P cross Q, but it could be an R cross F or any other 2 vectors. The X component, the Y component, and the Z component of our first vector. Below that we put the X, Y, and Z components of the second vector. and we follow this rule. We take this guy here, I, and we multiply it by, and we look at, since this is here in this column and row, we're going to multiply it by everything else. And what we're going to do is we're going to do multiply this way minus this way. So that means P, Y, Q, Z minus Q, Y, P, Z. Then we're going to say, okay, then we're going to go minus the next term, which is J, times, and now we're going to look and say, look, if we eliminate this row, we've got these two terms and these two terms, and we're going to do that same multiply this way, multiply this way. So we've got P, X, Q, Z minus Q, X, P, Z, J. And I've got the J to the left, it could be the right, no problem. Plus, and then we do our third one, K, and we're going to have, now it's these terms are that are left out, so it's Px Qy minus Qx Py. You'll notice this is the same result as we saw above. This is quick. You just set up your determinant. Let's say we're taking the cross product of two vectors. Let's call them R and S. In that case, we'd construct our little determinant. I, J, K. We'd say S, oh, we'd said R cross S, right? R cross S, that means we put RX, RY, RZ, SX, SY, SZ. We then are going to take this and multiply it times the quantity, this times this minus this times this. Then minus J, this times this minus this times this. Plus K, this times this minus this times this. So we see we set up I, J, K. This guy is multiplied by this operation. This, the last guy, is multiplied by this operation. And the middle guy is operated by that operation. Okay? That's how you do it. Make sure you practice this enough to nail it. You should be able to get this result here using either approach. Once you have gone through this math, multiplying out this and getting this, using both this method and this method, you then can select the easiest method, which will be this one, to solve it in general. And once you have mastered this, you can then go to the dot product vector, master that, and then you can come back to the main lecture 5 and learn how this applies to calculating moments. Make sense? This is a important tool. Now, it's true that this is not done a lot in industry. It's done when you're doing PhD work and master's classes and college classes. Or if you're doing a really high order, say orbital mechanics, you may get into some of this, dynamics, you may get into some of this. We need to learn these techniques because we're supposed to be trying to be engineers, but for day-to-day analysis, we're going to use a simplification of this with the PQ sine theta that we're going to learn about when we get back to the main lecture. Okay? Make sure you understand this before you go on. Otherwise, it will undermine any work you try to do in this class in the future that uses this principle. Enjoy.